Today I'm going to introduce the image-based classification of variable stars. First, results from optical gravitational lensing experiment data. Okay, and this is the content. First, we introduce the introduction, then the data sets, and then the method and model. Then the last is the results. Okay, first the introduction. Recently, machine learning methods have presented a viable solution for the automated classification of image-based data in various research fields and business applications. The automatic classification of variable stars using machine learning methods mostly uses photometric data sets where objects are represented by their light curves. However, so far astronomers have been mainly classifying variable star light curves based on various precomputed statistics and light curve parameters. In this work, we used an image-based convolutional neural network to classify the different types of variable stars. We used images of phase-folded light curves from OGLE3 survey for training, validating, and testing, and use OGLE4 survey as an independent data set for testing. Next, we'll introduce the data sets. Many catalogs of variable stars are available in the literature. Among these, OGLE provides one of the most extensive data sets, as it contains a sufficient number of labels and labeled samples to train and test our NNs. Here, we only focus on 5 different main variable star types observed in a large Magellanic Cloud field during OGLE3. So the chosen types were the following stars. Okay, first one is the anomalous Cepheids, is ACEP. Then the Delta Scutis, DCST. Next, the eclipsing binaries, the ECL. Then next, the fourth is the RR Lyrae stars. Then the last is the type 2 Cepheids, T2CEP. So these are the 5 types that we are gonna do on this CNN. Then here we converted the measure magnitudes of a given star into flux values with a 0.25. Then normalized the data with the maximum brightness using the epochs and periods from the OGLE catalog. The light curves have been phase-folded and transformed into 8-bit images with a size of 128 times 128 pixels with a black and white plotted dots. So it shows on the picture that these are the plotted dots. Then to increase the sample of underrepresented classes, randomly generated noise was sampled from a Gaussian distribution with zero mean and standard deviation equal to the given measured error, then added to the original light curves. The augmented data contained 125,000 images and 25,000 from each variable star type. So we can see on the picture here, these are the non-augmented data, the numbers of the non-augmented data, and these are the augmented data here. Okay. Next, we will so here the basic data augmentation methods usually use the Gaussian noise, elastic transform, random brightness, or contrast changes here. Okay, so next we will introduce the method and model. Here are the figures shows the schematic view of our CNN. The model has a conventional structure. It consists of 2 convolutional, 1 dropout, and 1 pooling. So here we can see this is 1 pair, and here 2 pair, 3 pair, and okay, 1, 2, 3, and 4 pair. Okay. So the resolution of input images is 128 times 128 pixels. The first two convolution layers use a 16 times 16 pixels with convolutional window. Here, so the first one here, we use the 16 times 16 with convolutional window, with 1 pixel stride to run through the images. After this step, the second, the third, and the fourth pair of convolutional uses 8 times 8, 4 times 4, and 2 times 2 pixel wide window. All convolutional layers use a ReLU activation. The output of the last convolution block is flattened and sent to a network of fully connected layers, and the last one is a softmax layer, which is used to normalize the output and hence yields predictions for all the 5 possible output labels. So here are the hyperparameters of our CNN, and in this experiment, here are the tested values that he experimented. So the first is starting convolutional window with 8 times 8, 16 times 16, and 32 times 32. He tested all 3 kinds of starting convolutional window, and the last he chose the 16 times 16 as the best result. Then the convolutional stride 1, and the tested value is only 1, and convolutional padding is 0. The activation is ReLU, and the dropout probability it tested 0.1 to 0.5, and at last the best result shows that the dropout probability should be 0.2. Then next, the pooling type is max pooling. The pooling size it uses 2 times 2 and 3 times 3, and at last it chooses the 2 times 2 pooling size. Next, the number of convolution layers it uses 8. Just like here you use 1, 2, 3, 4, 5, 6, 7, 8 here. Then next, the pooling layers is 4. So a pooling layer after there are 4 pairs of the layers, so there are 4 pooling. So there are 4 pooling layers in here. Then the number of fully connected layers are 4. And next, the fully connected activation functions, we all uses the ReLU function. Then next, the batch size, we uses 32 and 64 to do the experiments, and last, the 64 is much more better. Then the learning rate, it chooses between 10 negative 3 and 10 to negative 7, and it chooses 10 to negative 6. The optimizer, it tested the SGD, RMS prop, and the atom, and last it chooses the atom optimizer. And the last function is uses the categorical cross entropy. Okay, then here at last the results. So the final data set contained 125,000 images and 25,000 from each type, and the data was subdivided into 3 different parts: 70% and 15% and 50%. Is for the training, validation, and testing purposes respectively. So we can know that the number of images used for testing was 87,500 and 18,750 were used for validations. So here we can see the training and the accuracy and loss of the training and validation process. So here it stopped the training process after 173 full apples. So after the apple 173, we reached the 98.5% training accuracy for the complete model. Okay. So next we can see we do the test results for OGLE3 and OGLE4 data. So in the beginning, it tells us that we use the images of phase-folded light curves from the OGLE3 survey for training, validating, and testing. And we also use the OGLE4 survey as an independent data set for testing. So it wants to compare that whether that the CNN goes right or wrong. And here we know that after the training phase, the neural network was able to classify the different types between 80% and 99% and 77% to 98% accuracy for OGLE3 and OGLE4 respectively. And so here he made the two separate prediction tests on the model. And the first one ran on the previously mentioned OGLE3 data. So on the left side, this is the OGLE3 data. So So here we compare the two confusion matrices. It is clearly visible that our trained model works well and can classify variable stars from a different database. This is the row one. This is the actual type, and this is the predicted type. Yeah, if the actual is ACEP and it predicted ACEP, then it predicts 80.2% right here. So we can see at this line, every type that predicts almost is higher than 80%. And here we see the second results from we tested from the OGLE4 data. It also can show us that here is also doing well by our CNN model. So the two confusion matrix shows that the CNN trained on phase-folded light curves can classify variable stars with very high accuracy. So based on our results, we conclude that our model can efficiently distinguish between the ECL and periodic variables like RR light ray stars. So in this research, we focus only on the light curve shapes, but it will be possible in the future to insert other data into a more complex multi-channel network that could handle more input, image, and numerical data as well. Okay, so this is my report for this article. Thank you.